Hello and welcome everyone. My name is Mona Yadav and in this video we are going to learn about types of fluid and its rheology. So before starting with types of fluids and its rheology, let us first understand what is meant by fluid. So a fluid is a substance that flows and takes the shape of its container. So anything which flows, which is having a certain velocity and it can acquire the shape of the container in which it is stored, it can be termed as a fluid. In physics and engineering, fluids are considered to be the substances that can easily deform under the application of shear stress, which is a force applied parallel to the surface of the material. So in physics and engineering, fluids are considered to be the substances that can easily deform, that can easily take any shape under the application of shear stress. But this shear stress is a force which is applied parallel to the surface of the material. So there are two types of fluids basically, liquids and gases. So liquids are the one of the two primary states of matter along with solids and gases. Example of liquids include water, oil, gasoline. So these are all liquids. Gases are the substance that do not have a definite volume or shape, but examples of gases include air, oxygen and carbon dioxide. Basically many molecules are there and they don't have a definite volume or shape. They can be expanded or they can be compressed in a larger volume or in a lesser volume comparatively. So they can be compressed, they can be expanded. Now coming on to the fluid rheology. So rheo means flow and ology or logy means the study. So basically the study of fluid flow. Rheology means study of flow or fluid flow. So fluid rheology refers to the study of flow behavior of fluids. How a fluid is going to behave when it is flowing. So behavior of flow. So the study of the flow behavior of fluids and the relationship between the applied forces and the resulting deformation or motion of the fluid. So what is fluid rheology? In short, it is study of the flow, but in detail if we want to express, so fluid rheology refers to the study of the flow behavior of fluids and the relationship between the applied forces. So what happens if a shear stress is applied on a fluid flow? So how it is going to behave, how the flow is going to change. So the relationship between the applied forces and the resulting deformation. What kind of change is going to occur based on the motion of the fluid? It encompasses, that is it covers the study of how fluids respond to different types of stresses including shear stress, extensional stress and pressure. So under the action of pressure, flowing fluid is going to respond. It encompasses, that means it includes or it incorporates the study of how fluid responds to different type of stresses. So when a shear stress is applied, how that fluid is going to respond. When extensional stress is applied, how the fluid is going to respond. Or under the action of pressure, how that fluid is going to respond. So that is, these kind of studies are included in fluid rheology. In essence, or in short, rheological characterization quantifies the relationship between deformation, imposed stress, viscosity, flow behavior, elasticity, and recovery of a substance. So what is covered in rheological characterization? So it quantifies, it gives a quantity of the relationship between deformation, imposed stress, viscosity, flow behavior, elasticity, and recovery of a substance. Now classification of fluids. So fluids can be classified basically in two types, ideal fluid or real fluid. So ideal fluid is a fluid which is incompressible and having no viscosity, is known as an ideal fluid. Ideal fluid is only an imaginary fluid. Ideal fluid doesn't exist in the real world. So coming to the real fluid. So a fluid which possesses viscosity is known as real fluid. All the fluids which are used in real practice are real fluids. So basically with the fluids which we come across in our daily life or we are using them in industrial application or in domestic application or anywhere if we are coming across them, so those are the real fluids. Now let's see the detailed classification of fluids. So just now we seen that there are ideal fluids and real fluids. So ideal fluid doesn't exist. So what is the classification of real fluids then? So fluids are basically classified in two types, Newtonian fluid and non-Newtonian fluid. So Newtonian fluids are those, we will be seeing about it in detail, but still Newtonian fluids are those which follows or which obeys the fluids which obeys the Newton's law of viscosity come under the category of Newtonian fluids, whereas the fluids which do not obey the Newton's law of viscosity, they come under the category of non-Newtonian fluid. Now further, non-Newtonian fluids are classified in three types: viscoelastic, time independent, and time dependent. So time independent, so like when a fluid is flowing, so with the change in time, there will not be any significant change in properties of these fluids. So shear thinning with yield point, and shear thickening. These are the types of fluids under time independent. Whereas for time dependent, like when time is increased, so there can be change in certain properties of these fluids. So time dependent fluids are rheopectic and thixotropic. So these fluids, just now the fluids which we have seen under the category of Newtonian or under the category of non-Newtonian. So the behavior of these fluids, Newtonian fluid and various fluids which come under the category of non-Newtonian fluid, it can be plotted on a graph of shear rate versus shear stress. So here we can see that in case of Newtonian fluid, so the pattern is much directly proportional. With the increase in shear stress, shear rate increases, or with the increase in shear rate. With the increase in shear rate, shear stress increases, or with the increase in shear stress, shear rate increases. So the relation between the shear stress and shear rate is directly proportional or somewhat directly proportional, that can be seen in case of Newtonian fluid. Whereas for shear thickening or shear thinning with yield stress or Bingham plastic. So for these fluids, of course, the shear rate versus shear stress, they both are increasing. With the increase in one factor, another factor is increasing, but still the parametric difference is there. And now let us try to understand every type of fluid in detail. First of all, Newtonian fluids. So Newtonian fluids exhibit a linear relationship between the shear stress and the rate of deformation, that is velocity gradient. So in other words, their viscosity remains constant regardless of the shear rate. So whatever shear rate is applied, but viscosity is going to remain same. So Newtonian fluids are the fluids which obey the Newton's law of viscosity, and the relationship between shear stress and the rate of deformation, that is shear rate. So it is going to be a linear relation. So just now we have seen in the previous diagram that for Newtonian fluid, it is a linear relation between shear rate and shear stress. So examples of Newtonian fluids include water, air, and most common liquids and gases at moderate temperatures and pressure. So these are the fluids which come under the category of Newtonian fluids. These are the examples of Newtonian fluids. Newtonian fluids are characterized by a constant dynamic viscosity and they obey Newton's law of viscosity. Now coming on to next, that is non-Newtonian fluids. So non-Newtonian fluids do not follow Newton's law of viscosity and they exhibit a non-linear relationship between shear stress and rate of deformation. So we can see here in the diagram that just for Newtonian fluid there is linear relationship, but for non-Newtonian fluids the relationship is not linear. Even in case of Bingham plastic, here it is shown linear, but it is not ideally linear. The viscosity of non-Newtonian fluids can change with the applied shear stress, shear rate, or time. So with the variation in any of these parameters, whether shear stress is changing or shear rate is changing or time is changing, time is increasing, so there will be effect on viscosity in case of non-Newtonian fluids. Types of non-Newtonian fluids are shear thinning fluids, which are also called as pseudoplastic, shear thickening fluids, which are also called as dilatant, Bingham plastic, thixotropic, rheopectic. So let us start understanding about these fluids one by one. First of all, shear thinning fluids, also known as pseudoplastic fluids. So the viscosity of these fluids decreases as the shear rate increases. So this is a kind of inverse relation between viscosity and shear rate. As the shear rate is going to increase, the viscosity is going to decrease. Example include ketchup, shampoo, and certain polymer solution, that as soon as the shear rate increases, the viscosity, the thickening of these substances reduces, the viscosity reduces. So that's why they are known as shear thinning. With the increase in shear, the fluid starts thinning, that is, the viscosity starts decreasing. Shear thickening fluids, that is dilatant fluids, the viscosity increases as the shear rate increases. With the increase in shear rate, so with the increase in shear rate, the viscosity is going to increase. So here we have direct relation, directly proportional relation between shear rate and viscosity. With the application of more shear, the fluid is going to be thickened, that is, the viscosity is going to be increased. Examples include cornstarch mixed with water and certain colloidal suspensions. When shear rate is increased, for example, mixing is increased for these substances, so then they are going to be thickened. As soon as we are mixing it more, the thickness or the thickening of these substances will occur. So that's why we can conclude that viscosity of these substance is going to increase with the mixing, with the more shear rate. Next is Bingham plastic. So these fluids behave like solids at low stresses, that is at yield stress, and flow like fluids above a certain critical stress. So examples include certain types of mud and drilling fluids. So what are these fluids? These fluids behave like solids. They are going to behave like solid at low stresses, and they are going to flow like fluids above a certain critical stress. So this is some kind of extreme behavior, that at very low stresses they are going to behave like solids, and above a certain critical stress they are going to behave like fluids, or they are going to behave like liquids. So example include certain type of mud and drilling fluids. Thixotropic. Next fluid type is thixotropic fluid. These fluids become less viscous over the time when subjected to constant stress or agitation or mixing, but they regain their viscosity when left undisturbed. Examples include some paints, certain gels. So thixotropic fluids are the fluids which become less viscous. That means their viscosity reduces over the period of time when subjected to constant stress. So they are kind of shear thinning fluids, like with more mixing the viscosity is reduced, but they will regain their viscosity when they are left undisturbed. So if we are not disturbing it, if we are not mixing it, so they will regain its viscosity. So examples of which are some paints and certain gels. Rheopectic. So rheopectic are the fluid which behave in opposite manner to the thixotropic. So there are fluids whose strain rate is function of time. So fluids that require a gradually increasing shear stress to maintain a constant strain rate are referred as rheopectic. That means in order to maintain their viscosity, a continuous mixing will be required, so that the value of viscosity is maintained or their condition is maintained, otherwise they will be thickened. So there are the fluids whose strain rate is function of time. Fluids that require a gradual increasing shear stress to maintain a constant strain rate are referred as rheopectic. So basically rheopectic fluids are the fluids which behave in opposite manner to that of thixotropic. They need a certain continuous mixing or shear rate in order to maintain the value of their viscosity. Next, let us have idea about fluid continuum. What is the concept of fluid continuum? So the concept of continuum in fluid mechanics refers to the assumption that a fluid can be treated as a continuous and homogeneous medium without considering the individual molecules or particles that compose it. So basically we know that whenever a mass of fluid is there, so it is comprising of various fluid particles all together. But we can consider that when a fluid is flowing through a pipe, so these are not various particles, but they are the particles which are coming one by one in line, bonded together, so they can be considered as a continuous and homogeneous medium. So without considering the individual molecules, if we are not considering these molecules as individual ones, but we are considering them as a like chain like structure or particles that compose it, then we can consider that the fluid flow is nothing but the fluid continuum. The concept of continuum in fluid mechanics, actually it is a assumption. It is a assumed concept. Fluid continuum is a assumed concept that the fluid can be treated as a continuous and homogeneous medium. So this assumption is based on the observation that fluids consist of vast number of molecules or particles that are in constant motion, and they interact with each other through collisions. So when they are colliding, when they are interacting with each other, so then these fluid particles are in contact with each other. So when one particle is contact with another particle, and this whole thing goes on in the form of a cycle, then it is like a chain. So that's why we can consider that whenever a fluid is flowing, it is a continuous medium. So that's why we can consider it as a fluid continuum. So in the continuum hypothesis, the properties of the fluid such as density, velocity, pressure, temperature are assumed to be well defined at every point in space and time. So this means that the fluid properties vary continuously and smoothly from one point to another, allowing for the description of fluid behavior using differential equations. So basically, in short, fluid continuum is an assumed concept where we are considering the fluid flow as a continuous medium, continuous and homogeneous medium. So that's why we are considering it as, or we are terming it as, we are calling it as fluid continuum. Thank you.